Good morning, Science 10s. Today we are talking about potential energy. And so if you could please turn to Potential Energy Notes Guide. This is in your textbook on page 173 to 178 in case you're interested. So potential energy is just stored energy. It's a variety of different types. It could be elastic, like an elastic band. When you pull it, it's now changed shape and it's storing energy. Chemical energy and the bonds of chemicals. So like the meal that you had for breakfast this morning, gasoline, the chemical bonds, nuclear energy. So inside of a nucleus, there's energy in there. And of course, obviously, that one produces a huge amount of energy. That's why nuclear reactors produce so much energy. And gravitational energy. So it is due to the position of an object. And that's the one we're going to be talking about a lot today. So when we define potential energy, it's the potential or the ability to do work. And when we talk about this gravitational potential energy, our symbol is EP for potential energy, brackets grav, meaning it's due to gravity. So any object that you have, if it's above the Earth's surface, has gravity. So like in the little picture there, there's a man who is on a diving board. Well, he has energy due to his position. Now, just FYI, there is a difference between the mass and the weight of an object. Okay, mass is scalar, meaning that it's just kilograms. There's no direction. Whereas weight has to do to it's a vector, and so it has to do with the acceleration due to gravity, right? Gravity is pulling you down to the earth. And so this value changes, and so does the weight of an object can change. So the mass, let's say that you're going up to space, okay? So your mass is not going to change, okay? Mass is how much matter there is in a substance. On the other hand, the weight has to do with the amount of gravity. So, for instance, if you go to the moon, you're still the same amount of mass. You're still you, right? You haven't cut an arm off or something, right? You're still going to the moon. But the thing is different is your weight will be different. And the reason why, oh, I spelled weight wrong. Your weight will be different on the moon than on the earth because there's a different gravitational field. Okay, so it's a vector, right? Mass is just how much matter there is. Okay, I'm, whatever, 100 kilograms. Okay, when I go to the moon, it's not just how much mass I have, but it's going to be my weight based on the amount of gravity. And so there's a different amount of gravity on the moon than there is the earth. So you're still same amount of matter, but your weight will be different. So for this one, in your data booklet on page 6 is where we have this equation. Weight in newtons is equal to the mass times the gravity in kilograms. And so the gravity or the acceleration due to gravity, the G with the little arrow on it, that is 9.81 meters per second squared. That's on Earth. So again, if you're talking about on the moon, you'd have to be provided that information. So this is in your data booklet. It's on page 6. And so here's your data booklet, page 6. And they're showing you a couple of very important pieces of information. Here is the gravity due to Earth is 9.81 meters per second squared. And then this is just another way of saying the force due to gravity, or in other words, the weight that you have is m times g. Okay, so just a couple of reminders there. Force due to gravity. Sorry, my little arrows are off here. Okay, and so like we just saw in our notes, the weight is equal to force of gravity. These are equivalent, right? They mean the same thing. Force of gravity is the weight of an object, right? If the gravity changes, acceleration on due to gravity on the moon is different than that on the earth, then your weight will change. Your mass doesn't. Your mass is just the amount of matter. That will be the same. So gravity on earth is 9.81 meters per second squared. And just one more quick reminder, going back to our notes guide here, remember that we have these made up units, these derived units, and these derived units are also in your data booklet. These derived units mean like a Newton is made up of other units. Okay, so remember it is equal to 1 kilogram meter squared per, sorry, 1 kilogram meters per second squared. Okay, so when we look up, oh, I can't write today, 1 kilogram meters per second squared. Okay, meters per second squared. Okay, there we go. Second squared. Okay, so again, if you forget these derived units like newtons and joules, they are in your data booklet as well. Okay, and so I'm just going to go back to your data booklet and then I'll talk about our examples. Okay, so back here for just a second. Here's our derived units. And just ignore this on how to get full marks for just a second. Derived SI units, we've got force in newtons. A newton is a kilogram meters per second squared. Energy in joules, made up of a newton meter, which is the same as saying kilogram meters squared per second squared. So remember, you have your data booklet. You have this page 6. You're good to go. Okay, so we're going to go and do a couple of examples, and our examples are written out for us in our notes guide. A reminder, every time you are doing a physics problem, to get full marks, you have to start by writing out the formula. Now, honestly, I think that you need to not just write out the formula, but write down all what you're given in the question. And I think that even though you're not awarded marks for that, that helps you organize your answer. If you don't do that, I find that you will struggle, especially if you have to rearrange. So here's an example of finding the weight or the force due to gravity, Fg. Okay, and again, that's in your data booklet, and that is something that you can always look up. So what are we given in the question? Well, we're given a mass of 50 kg. So units are kg, and that's 3 significant digits in that value. And we are on Earth. And so because we're on Earth, we know the acceleration due to gravity, that's in our data booklet. This is also 3 significant digits. What would the person's weight be? So what would their weight be? Well, the weight or the force of gravity is equal to mg. We look that up, we write it out. Then our next thing is, after we've written out our formula, weight or force of gravity is mg, we substitute in our values. So we've got 50.0 kilograms, don't forget to show your units, times the acceleration due to gravity, 9.81 meters per second squared. Do the math on your calculator. 50 times 9.81. So on my calculator, I get 491. And then my last step is writing out my answer. And as part of that, you have to have correct sig digs. Okay, so we're going to have 3 sig digs in this answer. Correct units, so kilograms meter per second squared, that's the same as a newton. Remember, that's a derived unit. Rounding, didn't have to round that one, we're all good. This one, you can always do scientific notation. If you would like to instead write this as 4.91 times 10 to the 2 newtons, that is always acceptable to write in scientific notation. Okay, so next video, I'm going to do a couple of examples of gravitational potential energy, how to calculate EP grav, which it's the same as the work being done. So it's equal to force times distance, or like it says in your data booklet, mgh, mass times the gravity due to acceleration times the height. So I'm going to do a couple of examples of this in our next video.